Right. If everyone can start looking at the dancing goats. Right. So the topic for today is oscillations, and those goats are literally oscillating. Take a look at them now, enjoy it while you can. The rest of this lecture you'll be having masses on springs oscillating. This is a little more entertaining. Now, what I do want to focus on for those goats, of course, is look at their motion. Right? An oscillation is that. It's a back and forth motion about some equilibrium, about some center position. Correct? So today we're going to start the next topic, which is oscillations, and I'm going to preface this by saying the next two topics are mathematically challenging. So instead of doing the math, we're going to try and understand it more conceptually than mathematically. Okay, so stay with me on the concepts. The idea here is to try and understand this kind of motion. Right? It's an oscillation, which means it's a back and forth motion about an equilibrium. Okay? Now, the first question you should ask yourself on seeing the dancing goats, well, after you ask whether they were harmed during the making of this video, which I believe they weren't. Right. The second question you should ask yourself on seeing the dancing goats is why are they oscillating about such a position? Right? So, obviously, when they're at some displacement from equilibrium, there has to be a force pulling them back to the equilibrium position. Correct? Right? That's why they're going back. They're not at one edge. Right? We call those kinds of forces which try and restore an object back to its original shape restoring forces. We're not very imaginative in calling them that. Now, the reason oscillations are important, the most basic reason oscillations are important is actually the second one. Right? Oscillation, it's a back and forth motion which takes a fixed amount of time. Right? So that is literally how we measure time. Right? In order to measure time, you need to have something that is completely reproducible, so it takes the same amount of time every single time. Right? So you can break time up into these little chunks. Everyone following me? And that's what an oscillation does. Right? For a lot of these oscillations, the time for an oscillation is fixed. Right? So if you count the number of oscillations, and you know the time for a single oscillation, you know how much time has elapsed. Right? So that's literally how you measure time. Okay? The other, of course, there are many applications of oscillations. One of relevance to you guys is magnetic resonance imaging. So MRI, right? Basically, you stuff a person in a really big magnet and you get an image. The reason for that image is hydrogen, which is essentially just a proton, oscillates at certain frequencies depending on its local environment. Right? So most of you are, well, all of you are mostly made up of water. Right? Which is essentially hydrogen, it's protons. Right? You put these protons in a big magnetic field and then you excite them with an oscillation, and then they oscillate at specific frequencies which correspond to their natural environment. So hydrogen in blood versus hydrogen in different kinds of tissue oscillates slightly differently. Right? So you can tell based on the oscillation what it's oscillating in, hence you can create an image. Obviously, the process is a lot more complicated, but that's the basic idea, right? What you're imaging when you're imaging MRI, right? Like, what you're actually imaging is hydrogen, right? The actual hydrogen environment. Everyone following me? Okay, so oscillations are important, and they present a bit of a challenge. So, this is a simple mass on a spring, right? For our purposes, we're going to assume that all the mass is in the block. So all our springs are going to be light and massless. Right? So we don't worry about the spring's mass. We only worry about the mass attached to the spring. Okay? Now, when I have a mass attached to a spring like this, right, that center line that I've called equilibrium is the unstretched position of the spring. Right? When I stretch a mass from that position, the spring is going to try and take that mass back to its original position. Everyone following me? right? That kind of force, the force it exerts on this mass, is a restoring force. It's called a restoring force simply because it's trying to take the object back to its original position. So if you look over there, right, the mass is over there, the spring is going to try and take it towards equilibrium. Everyone following me? Now, the nature of that force, the mathematical nature of that force, is given by that relationship. It's F equals minus kx. We call that Hooke's law, right? Various objects in their elastic limit will obey Hooke's law, right? Which basically means that the amount of deformation, right? The more the deformation, the more the force trying to restore it back. Right? So if you look at that expression, what it's telling you is that the force, the magnitude of the force increases with x, and x is displacement. Right? So the more stretch or compression I have in a spring, the more force the spring is exerting on that system to try and take it back to original position. Everyone following me so far? Okay. And that, of course, presents a challenge. Right? So, anyways, we call forces that obey Hooke's law restoring forces, and the resulting oscillation which occurs is called simple harmonic motion. Right? It's a misnomer. There's nothing quite that simple about simple harmonic motion. It's SHM is the short form. So, essentially, what we're saying is an object under a restoring force will experience simple harmonic motion. Okay? Those are like the terms involved. Now, to study this motion, one looks at that force and one finds that the force depends on displacement. Right? So, as the object is moving through its path, right, is the force on it constant? If the force depends on x, right, F is kx, correct? If the force depends on x, as the object is moving, x is changing. Right? X is the object's displacement. Right? Which means that the force on the object is changing. Does this make sense? Which presents an issue. I'll come to that. He asked what's k. I'm going to come to that. Okay. So that dependence of f on x, right? That f is dependent on position, right? Makes this force not a constant force. Right? So if I'm going to talk about the position of the object, the velocity of the object, the acceleration of the object, right, to describe the motion, I can't talk about the kinematic equations which we've been using so far. Right? Because all of them had that big assumption that acceleration needs to be constant. Right? A non-constant force does not produce a constant acceleration. It produces a changing acceleration. Right? F is still ma. Right? So all that kinematic stuff does not apply, which is why this becomes mathematically difficult. Right? And we'll see how to tackle that. Now, the question on what k is, right? K is in the F equals minus kx expression. K is the spring constant. Right? It is a measure of how stiff that spring is. Right? Different springs require different forces to stretch. Right? You have stiffer springs and looser springs. Correct? A high k value means it's a stiff spring, right? So there's a lot of force for a little displacement, right? A low k value means it's an easy spring to stretch, right? You don't need to apply a lot of force to stretch a large amount. Everyone with me? The way k changes is by changing the spring, okay? Now, this is what the object will do. Right? This slide shows you what that object is going to do, and it's actually better if we look at it this way, right? Actually moving. So, if you look at the three vectors on that diagram, that's an object. It's a mass m attached to some spring constant k, spring, and no friction. Okay, so it's going to oscillate back and forth, right, about some equilibrium position. Correct? Okay. Now, look at the displacement, right? Displacement is measured from equilibrium, right? So it's just a measure of the changing position of the object, right? V, of course, is the velocity of the object, right? And if you notice the green arrow, its size is changing, its direction is changing constantly, right? During this entire motion, that green arrow, which is representing V, right, is continuously changing. right? Which means this system is accelerating, right? However, if you look at A, that is also constantly changing, right? So this system is undergoing non-constant acceleration, right? Okay, so when you stretch it in the beginning to one end, right, and then you let go, the reason it goes back to its original position is there's a restoring force on it at the end, right? Whenever the spring is stretched, there is a force trying to pull it back to equilibrium, right? Okay, so there's that force trying to pull it back to equilibrium. So it comes back to equilibrium. Why does it go to the other side? Not the K. Why does the object not come back to equilibrium and stay there? Velocity, inertia, right? It has inertia, correct? On its way back, when it's at the equilibrium position, right, where there's no force on it because the spring isn't stretched, right? At that point, it's actually moving. Yes? As it's passing through the middle, it's actually moving, right? If there's no force on it at the middle, it's going to keep moving, right? That's inertia. So it overshoots the equilibrium position, right? And as it overshoots, it starts compressing the spring, right? So the spring starts pushing it back to equilibrium, so it slows down, right? And then the same process occurs. Spring pushes it back to equilibrium, it's moving at equilibrium, overshoots equilibrium to the other end, right? Again, the same thing, spring stretches as far as it can to slow it down and turn it around and move it back, and it overshoots again, right? So it will keep doing this process. This makes sense? And that is an oscillation, right? That is simple harmonic motion. It's a repetitive motion occurring after a fixed amount of time all the time, right? So our aim for today is to try and describe the velocity and acceleration of this object, right? Which is difficult. You can see it, right? It's not quite that straightforward. The easiest way to tackle situations where A isn't fixed is still energy considerations, right? Remember, when we did conservation of energy, that's always true, regardless of whether the forces are constant or not, right? I should be able to conserve energy. This makes sense? The total energy in this system should be fixed, right? Which brings us to spring potential energies in a bit. Okay, a few things. Displacement, right, is measured from equilibrium. And the definition of equilibrium is the position at which there is no net force on the object, right? So in this case, where it's a horizontal spring mass system, equilibrium is where the spring is unstretched, because that is where the force on the object is 0, right? F is still minus kx. Okay? Amplitude is the maximum displacement, right, from equilibrium. Okay, so I have an equilibrium position, which is what it's going to oscillate about. The amplitude is described as the maximum displacement from equilibrium, right? So that's my center. I go to one end, come back here, go to the other end, right? This much from the center to one end is the amplitude. Okay? A cycle is a full to and fro motion, right? So it's one complete oscillation, right? So if I start from here, a complete cycle is go all the way to one end, come back, go all the way to the other end, and come back. Everyone with me? That's how we define one complete cycle. The period is the time taken for that cycle to happen, right? So in order for this object to go from here, come back here, go here, come back here, it took a certain amount of time. We call that the time period of the oscillation, right? And frequency is the number of cycles in 1 second, right? So it's just the inverse of the time period, right? If this process going from here to here and there to there, right, that takes 2 seconds, let's say, right, then the number of cycles in 1 second is half a second, right? It's 1/2. Everyone with me? If this process took half a second, then the frequency, which is the number of cycles in 1 second, is 1/2, so it's 2. Does this make sense? Right? Frequency and time period are inversely related. It's F equals 1/T. Okay. Let's see if you guys are awake. Remember, amplitude is described as the total distance from the equilibrium position, right? The total displacement from equilibrium. So, how many amplitudes are covered in one time interval t? One time interval t is the time taken for one complete oscillation. So, what is the actual distance traveled by that mass in one complete oscillation? The displacement will be 0, right? In one complete oscillation, it's back to where it started, right? But the distance is not 0. Do I dare to look? Very good. I should be seeing people's hands do this. Count. How many A's? Very good. Some are getting it. Do it with your hands. It doesn't matter. It looks like a weird dance move at 8 in the morning. It's okay. You start from equilibrium, right? You go to one end. How much distance have you covered? A, right? That's the amplitude. You go back to equilibrium, you have covered another A. Correct? Now you have to go the other side. You cover another A. And then you come back. How many A's did I cover? Does this make sense? Right? Since amplitude is defined as distance from equilibrium, in one complete cycle, this object has actually traveled 4 times the amplitude. Right? So click the appropriate response. Good. I'm going to close this. Now look at what I'm asking. It's an object undergoing simple harmonic motion with amplitude A and time period t. At what location are V and A simultaneously 0? What is true of an object if it has a simultaneous V and A of 0? What's it doing? It's not moving. It's at rest and it's staying at rest. Is this object doing that? No. Right? So in SHM, there is no location where V and A are simultaneously 0 because that would mean the object isn't moving. Right? In simple harmonic motion, what happens is that where A is 0, V is non-zero. Right? That's why the object keeps moving. Right? A is 0 where force is 0. So it's 0 at equilibrium. Right? The only reason the object keeps moving is when it's passing through equilibrium, it has a V. Right? So there is nowhere for SHM that V and A can simultaneously be 0. Right. Good. Click something. Now let's get to energy. So, like gravitational potential energy, when you stretch or compress a spring, you store energy in that stretched or compressed spring. Okay? So that is an energy stored in the system, in the configuration. Right? Because a stretched spring or a compressed spring has the ability to do work. Everyone following me so far? So just like gravitational potential energy, right, which was the energy stored in the gravitational setup of a system, right, like some things at a height and can fall, right, similarly, a stretched or compressed spring stores a certain amount of energy. Right? The amount of energy stored depends on how much that spring is stretched or compressed. Right? The more it's stretched, the more energy I store. The more it's compressed, the more energy I store. Right? Because it takes work to stretch and compress a spring. Right? And that work that you're doing to stretch the spring or compress the spring is what's stored in that spring as potential energy. Everyone with me? Okay, so if a spring is stretched by an amount x and the spring has spring constant k, the energy stored in it is 1/2 kx squared. Okay, measured in joules. X is displacement measured from equilibrium, the unstretched position of the spring. The kinetic energy, of course, is in the block, right? The block that's actually moving, oscillating. It has a V, so it has a kinetic energy. It has a mass and a speed, right? Its Ke is 1/2 mv squared. Okay? The total energy, if we neglect friction, will be conserved. So what we're saying is the total potential energy in the spring plus the total kinetic energy in the spring during its entire motion, right, is conserved. There's nowhere for it to go. You can just translate between potential energy to kinetic and kinetic to potential, right? You're allowed to transfer between different forms, right, but it doesn't leave the system. There's no dissipative force in this. Okay? So, after a little bit of algebra, which we will actually do, what you'll find is that u plus k is equal to 1/2 Ka squared. Now, before we go forward, this is one of the important things for next semester. Right? What we're saying is that the energy stored in an oscillating system, right? This is a block of mass m, which is oscillating back and forth, right? Which has some total energy. So that total energy is in this system, correct? Right. What we're saying is that the total energy stored in the system is 1/2 Ka squared, right? So it depends on the square of the amplitude. This makes sense? Right? A is the maximum stretch, right? It's the total, it's the amplitude of the oscillation. So larger amplitude oscillations store more energy than smaller amplitude oscillations. Everyone with me? For the same spring. Right? The larger K obviously leads to larger energy. This is a stiffer spring. Okay. So remember that. The math will come back later. But remember that for next semester, okay? That the energy stored in an oscillation is proportional to the square of its amplitude. Okay, let's try conserving energy. So the idea with conserving energy is, let's say I start from a compressed position of the spring, right? At that location, right, the spring is just compressed. Is the block moving? No. So all the energy in it must be potential, right? And that is 1/2 K times the square of the displacement. And since it's at an edge, right, it's not moving, right? Since it's at an edge, that displacement is A, it's the amplitude. This makes sense? Okay, so at that location, it's all potential energy. Then you let go, it starts moving, right? It's going to move back towards equilibrium. When it's passing through equilibrium, what is the stretch in the spring? 0. So what is the potential energy stored in the spring? 0. So what happened to all that potential energy? Became kinetic, right? At equilibrium, all the energy is kinetic. This makes sense? So it's moving fastest where? At equilibrium, right? Every time it moves away from equilibrium, right, even a little bit on either side, there is a force acting on it, slowing it down, getting it to try and go back. This makes sense? Because the spring is now either stretched or compressed. Anytime you're not at equilibrium, right? Okay, so at the equilibrium position, it has a V, so it has K, and it's all kinetic since the spring isn't stretched, and because of that, it'll keep going, right? At that location, there's no force on it. It has a V, it's going to keep going, right? Goes all the way to the other end. It stretches the spring such that all the potential, all the kinetic energy it had in the middle is now potential energy again at the side. This makes sense? This also tells you why, about equilibrium, the oscillation is equal. Right? Because how much energy you have on one end, you have to have the same amount of energy on the other end. So it's the same amount of stretch or compression at each end. Right? So A is equal about equilibrium. Right. At this point, it will, of course, only have potential energy. Then spring pulls it backwards. Now it's moving in the other direction, but at this location, it still has all kinetic. And then now back to my original position, right, where again it's all potential. Right? So all that's happening energetically during this process is energy is going from potential energy in the spring to kinetic energy in the mass, back to potential energy in the spring, back to kinetic energy in the mass, and so on. Right? It's just the energy in this system is trapped. Right? It's fixed. It's just allowed to change forms. Okay? Not allowed to change, leave the system. Right. So the total mechanical energy stays the same, which is something we can use. Right? This is why the total energy stored in the oscillation is 1/2 Ka squared. Because at either end, the stretch is A. Right? The amplitude is A. Correct? The K is 0 because it's not moving at each end. So the total energy at any end is 1/2 Ka squared, which means the total energy at any point during the motion must be 1/2 Ka squared. Right? The sum of potential plus kinetic is constant. So whatever number it is at each end, it's the same total number everywhere. Everyone with me? Right? It's just that at the ends it's potential, in the middle it's kinetic, and everywhere else it's a mix of kinetic and potential. Right? This mass is moving and the spring is stretched or compressed a little. Okay, so we can't talk about a specific V, right? Since V for this object is constantly changing, right? I can't talk about V as just one number, right? It's a range of numbers. It goes from 0 at the ends to its maximum in the middle, right? So we can talk about V max. Okay, so if you look at this expression, the total energy is 1/2 Ka squared. The next two terms, this is at any random location in the object. It has a kinetic energy of 1/2 mv squared and a potential energy of 1/2 kx squared. Correct? Okay, that total must equal 1/2 Ka squared. Right? Because all we're saying is sum of potential plus kinetic at any point in this object's motion is the total energy of the object. Right? So you can solve that to get a Vmax, which is the velocity of the object at equilibrium. Don't worry about the algebra. I do not expect you guys to do the algebra on this. Okay? It's just there for completeness. What I want you to look at is that Vmax. Right? So that Vmax is under root K over m times A. Right? Where does this object have its highest speed? At equilibrium, right? At the midpoint. So that is the speed of the object at equilibrium. This makes sense? It is how fast the object is moving when it is passing through equilibrium on each side. Right? It depends on K. Right? The higher the K value, the stiffer the spring. So the faster the thing is moving around equilibrium, right? At equilibrium. Right? Because there's a larger restoring force trying to bring it back. Right? The larger the value of m, the slower it gets, because the larger a value of m, the more inertia it has. Right? A lot more force is then expended in turning it. Right? And then speeding it up. Okay. And A, of course, is the amplitude. Now, for a little bit, I'm going to have you guys imagine stuff. So, let's say that I put a piece of paper which just rolled across as that mass underwent simple harmonic motion. Right? So that mass is oscillating up and down. Correct? Okay. If you were to put like a pen on it and a piece of paper that rolled underneath it, it would trace out a path that looks like that. Right? The red line. Correct? Can anyone recognize that function? What is that function? It's a sine or a cosine. It's a sinusoidal curve. Right? Anyways, we'll get to what that actually means. What I want you to do right now, of course, is answer a few questions. So what this graph is doing is it's showing you that red curve, right? So it's basically a plot of displacement of this object as a function of time. Right? Okay. Now, the question is actually asking you, what time is the potential energy of the block 0? So, what needs to be the stretch or compression in the spring for the potential energy of the block to be 0. Where is the potential energy in this system 0? At equilibrium, right? Where it isn't stretched. Correct? So now look at that graph, right? It's a displacement versus time curve, right? And identify which of A, B, C, or D corresponds to a 0 displacement position. Good. Right? Because you're plotting displacement as a function of time. Where displacement is 0 is A. Right? That is equilibrium. Correct? Okay. So click the appropriate response. Let's keep going. Same setup. This time what I'm asking you is, where is the potential energy of this block maximum? What is my condition for potential energy to be max? Should the spring be stretched the least or the most? The most, right? Potential energy stored in the spring in the stretch or compression of the spring. Right? So what I'm looking for when I look for maximum potential energy is maximum displacement. Right? The edges. So, which time corresponds to the block being at an edge of motion? C, right? Correct? And notice it's minus A, right? Which doesn't matter because the energy stored is 1/2 Ka squared. Right? Minus A squared and A squared are the same number. Right? So, the potential energy is max at the ends, which is this point right here, right? Which corresponds to this time period. Right? So, let's see. Very good. Right, I'm going to keep my mouth shut and you guys are going to answer this. It is very hard for me to keep my mouth shut. This won't last, so do it fast. So K is max where potential energy is least, right? Because K plus U is fixed. So where is the potential energy the least? Or where is the block moving fastest? Yes, good. At A, right? The equilibrium position. That's where kinetic energy is maximum. Right, so click something. And we're going to try one more, I believe. Yes. Again with my mouth shut. Very good. Great. So everyone seems to be pretty okay on this. I'm guessing you guys are getting an idea for the next set of conceptual questions on the exams. Okay. So yes, kinetic energy of the block is 0 at either end where it's turning, right? Which is also where potential energy is maximum. Right. Now I need you guys to look at this video carefully. It's actually GIF, but anyways. The idea here is to try and, we're still trying to understand simple harmonic motion, right? We need to be able to talk about the time it takes for one complete oscillation, right? Ideally, I'd love to be able to use some math and calculus to get to that answer, but that's messy and kind of hard to understand, right? Conceptually though, simple harmonic motion can be related to a motion that you're fairly familiar with, or should be fairly familiar with, right? Rotation, right? Revolution, moving in a circle at a constant speed. So if you look at these two objects, right? One is a mass and a spring oscillating up and down. The other is a ball moving in a circle at a constant speed. Okay? The second motion, moving in a circle at a constant speed, is something you guys have spent 3 weeks analyzing, torturing yourselves over, probably cursing me. It's not my fault. Right. What I want you to do though is look at the vertical position of that green ball and the red block as they move. Look at their vertical position as they move, and you should find that it's the same. Right? The vertical position of that green block, the ball, right, is the same as the vertical position of that red box, right, which is oscillating. This makes sense?
So you had mentioned that the ball is moving at a constant
speed. Yes.
But can you tell us that when the spring is oscillating,
the spring speed is not the same.
Okay.
Right? It's not. The block that's moving up and down, right? It has zero velocity at the top, zero velocity at the bottom, max in the middle, right? The circle being described is being described at uniform speed, but the vertical position of the blocks of the ball in that circle is the same as the vertical position of my mass spring system. Does that make sense? Okay? And that is this, right? What this is telling you is that if I were to just look at an object moving in a circle and just look at one of its components, right? Either the x component or the y component, right? Just how its x position is changing as it moves in a circle, or in this case, how its y position is changing as it moves in a circle, right? So in order to understand this curve, what I want you to do is look at the circle on the right, which is being described, right? That's the black thing moving in a circle with constant velocity, right? Constant speed. And the red dot, right, on the y-axis is that thing's projection on the y-axis, right? And that is SHM, right? That is undergoing simple harmonic motion. To look at it another way is look at this figure, right? So you have an object moving in a circle, right, with a constant speed. Let's say you look edge on, right, with no depth perception, right? Then for you, that object is moving back and forth. Correct? And at the edges of that motion, its velocity in that direction is zero, even in the circle. Does this make sense? Right? So it's one component of speed. Now the reason this is important is that if we can relate, right, circular motion to simple harmonic motion, I can find the amount of time taken for an oscillation. Because if you look at this curve, like this again, right, the amount of time taken for that thing to go up and down, right, one complete oscillation is the same as the amount of time taken for that ball to move in a circle once. This makes sense? Right? Now, I can find how fast the ball is moving in the circle, right? It's moving with some speed v. It's covering the circumference of the circle, which is 2 pi r, right? So, if I want to find the time taken, I can divide 2 pi r by v. Quite straightforward, right? You've done this before, right? The other way I can think about it is in terms of angular speeds, right? Omega, remember that? Have we all blanked out omega from our heads? Okay. Omega is the rate at which the angle changes, right? Right? It's the angular speed of an object. The object on the right has some fixed omega, right? It's moving at a constant angular speed, right? How much angle is it describing in one circle? How much angle does this object describe in one circle? What is the total angle in one circle? 360 degrees, or in terms of radians, 2 pi, right? So, we can write that the time period is 2 pi divided by omega, correct? Everyone agree? Right? Okay. Omega is the angular frequency of this object. Everyone following me so far? And if you guys remember, well, you should remember this one, V is equal to R omega. Right? For an object moving in a circle of radius r, V is equal to R times omega. This makes sense so far? Okay. Now, I'm going to go back to the picture. In terms of the amplitude of this oscillation, right? The red thing is oscillating. In terms of that amplitude, can someone tell me what is the radius of that circle? What is the full length of the oscillation? A or 2A? 2A, right? End to end is 2A, right? And that 2A is the diameter of the circle. Correct? So what's the radius of this circle? A, right? Okay. Let's go back here. So we can rewrite V for that circle as A times omega. This makes sense? Correct? Right? It's moving in a circle of radius A with an angular speed omega. Everyone with me so far? Okay. Now what I want you to do is look at what we had earlier from energy considerations for the max speed of the object. Right? It's under root k over m times A. Right? And this are the same thing essentially. Right? It's that projection of that circular motion onto that axis. Right? So to complete our analogy, right? This is an analogy. An object moving in a circle is not an object moving up and down. Right? But it's taking the same amount of time. This makes sense? To complete our analogy, this Vmax and this V can be related if we say that the omega for this oscillation is under root k over m. Does everyone see that? That I can relate this V to this V, right? A is the same, correct? Right? So these two are the same if this under root k over m is omega. Everyone with me so far? We following this? Kinda? All we're saying right now is that the amount of time taken for one complete oscillation is the same as the amount of time taken for one complete revolution, right? For those two systems that we had up on the board before. Correct? Okay. Now what we're doing is trying to find a relationship between the amount of time taken for the object to move in a circle, right, which is the total angle covered divided by the angular speed, right, and the time taken for the complete oscillation. This makes sense? Right? Because they're the same. So if I can find one of the times, I can find both of the times. Everyone with me? Right. I can find the one for the circle, right? It is that much. Right? If an object is moving in a circle with angular speed omega, it's describing 2 pi in one circle. Right? So the time taken is 2 pi divided by omega. This makes sense? Okay. So if this is omega for the spring mass system, the time taken is 2 pi under root m over k. Does this make sense to everyone? This is still the same thing. It's 2 pi divided by omega, but omega for the spring mass system is under root k over m. Right? So the inverse of that, 1 over omega, is under root m over k. Everyone with me? Okay. So if that is the time period, the frequency of the oscillation, which is the number of oscillations in 1 second, is 1 over that number. Right? It's the inverse of the time period. So f is 1 over t, which is 1 over 2 pi under root k over m. Right? And I don't need to have you read my writing. I'm pretty sure I put this on the slides. Okay. So the angular frequency of the spring in comparison to an object moving in a circle is under root k over m. Right? That's the angular speed. From there, we can relate to frequency and time period. So the time period is 2 pi under root m over k. The frequency is 1 over the time period, right? So it's just the inverse of that. Now, the point here, right, is we were able to use rotation, like circular motion, right, to come up with the time for the complete oscillation. Right? That's all. That's literally the only thing. Right? There are other ways to do this, but they're more mathematically complicated. Right? Conceptually, though, there is no difference between an object moving in a circle, if you would just consider its x or y component, and moving in simple harmonic motion. Right? So when an object is moving in a circle, its two components, its x component and its y component, are actually undergoing SHM. Right? They're oscillating back and forth about the middle. Right? So think about an object moving in a circle like this, right? Correct? If you have no depth perception, right, this way, then as far as you're concerned, this object is doing this. Right? And that is SHM. This makes sense? Okay. Don't worry, we have another week on this before we enter waves. Before you leave, this is the actual math for this. I do not expect you guys to know this. Your book has it for completeness, but you can describe position, velocity, and acceleration mathematically.
Topic for essay is due rotation today.
Yeah.
Do you want a printed version of that? Or, because on the side it said either printed or email, so I have it on my computer.
Yeah.
So can I just email it to you? Okay, cool.
I'm having problems with the clicker leaf on my phone, the app on my phone.
Which Wi-Fi are you on?
I'm on the EDU roam. But
What's the problem? It's kicking you off?
Yeah, and then it's like not recording my answers. I already sent you an email because I noticed at like 8:30, and I was like, oh, okay, it says no
Fine,
answer.
send me an email, that's all.
But I started using
with
it on my laptop and it was fine. So I think I'm just gonna like use it on my laptop from now
probably
on.
safer. Yes.
Hi. I wasn't able to sign on to Booker at all today.
Email me
Okay.
with your name. It's fine.
Okay, great.
Hi.
I mixed up the assignment with today. I did the paper topic due today, but I forgot the
Homework?
lecture.
You forgot the pre-lecture.
Yes.
I don't extend pre-lectures, but I do drop the lowest too, so don't miss more and you'll be fine.
Oh, okay. I didn't have a mistake. Okay, good. Thank you.
Yep.
Do we still have an exam the upcoming week, not next one, but the following one?
Whenever it's on the schedule.
We still have it, right? Yeah, okay.
It just didn't let me
Email.
answer to.
Email's fine.
Yeah, my clicker just stopped
Email?
working. Okay, thanks.